And this will allow me to make a small comparison of how cells are actually contracting compared to muscles at a very different scale, and actually go to the energy budget of how much energy goes into the cell and is dissipated during the process, and how much is useful. And possibly I'll tell you about nonlinear extensions if I have an extension. Okay, so my original motivation was that, cells come in all sorts of shapes, and actually the same cell could adopt very different shapes depending on the environment it is faced with. For instance, when suspended, they take a very nice spherical shape, but then elongate to that shape, for instance, on a flat substrate. They take this nice hexagonal lattice structure we've seen in the previous talk when packed with their neighbors, and they could also take very weird shapes like in the Drosophila eye here. So, as a mechanicist, I was wondering how can you build possibly a structure with a building block that doesn't have the right shape. So what we know from experiments is that the shape of the cell does adapt, and that its internal structure also reorganizes. And you've seen beautiful experiments on patterns which are showing that. But then this doesn't really tell you which of this reorganization and shape change come first, and how they interplay, and especially how, from the molecular structure that we know, we get the macroscopic, mesoscopic shapes that we observe. And we can do, for instance, we've seen a beautiful phenomenological modeling of that in the previous talk, but I'd like to make the link with the molecular structure behind that from a rheological point of view. So what we also know is that the rigidity of the substrate, of the environment, matters a lot. So if you vary the stiffness of a flat substrate on which cells are adhering with the same cell type, so the same biochemical phenotype spreading in them, will give a very different morphological phenotype of the cell, and a different arrangement, a different structure also of the actin especially. So, that could be quite intuitive for us, because when we are working on a hard substrate, it's very different from actually wading on a muddy, squishy substrate. And we could guess that the mechanics will be different, but we still need to explain that. And also, I'd like to point that, to remind everyone that rigidity is not a very easy property to actually monitor. For instance, just looking at this screen, I don't know whether it's soft or hard. I need to push on it and exert some level of force and measure how much displacement I get from this force. So cells actually need to act and transmit force to the substrate in order to sense the rigidity, and that's the whole question: how do they do that?
Your microphone just went off.
Oh, okay.
Maybe it's
Is it
on the
on?
other side of your shirt.
Not a problem for us, but
Yeah.
the same for the screen here.
Is it better?
No, it's off. Maybe it's electronic.
Battery, maybe.
Maybe it's a battery. Yeah.
Battery off.
No, there's no low battery. Is the microphone working?
He's bringing another. Oh, well.
All right. So, So I was saying that rigidity matters, and in order to explain it, we would like to. Well, we would need to understand this whole machinery that we now see much better in 3D, thanks to spin microscopy for a few years. And, well, this is the role between the focal adhesions, which are actually in contact directly with the substrate and could sense the stiffness of that substrate directly, but also understand how the cell spreading stops earlier when you are on a softer substrate, which makes things complicated. And even more complicated than that. This system is always moving, so you see that even, well, we've seen a couple of times these retrograde flows, so even when the cell is sitting on the substrate and not progressing, there is this retrograde flow of its material. So in order to link this structure with the actual shape of the object, we need to account for this never-ending flow, because actually even when the cell is immobile, so with fixed adhesion points in this, unfortunately, not well clothed paper by the sheet group, you still have retrograde flow everlasting, while the cell edge is not progressing. Okay, so how does this all work? This is quite complicated, complicated geometry, and also it's difficult to measure forces on that, although traction force microscopy can do that through an inverse method. So I was very happy to see the experiment by Etienne, who is actually having two long microplates made of glass, and he grabs a cell when it's still suspended and lets it adhere on these fibronectin-coated microplates, and this is what it gives. If you have a sufficiently flexible, so long microplate here, the cell will actually deflect them. So I'd like to stress that here we don't impose the displacement, we don't impose the force. It's not Dirichlet boundary conditions for the mathematicians, it's not Neumann boundary conditions, it's the stiffness of the apparatus which is fixed, which means it's a link between the displacement and the force. Okay, so it's really the stiffness which is set. And we measure this evolution of the deflection of the top microplate or of the cell line equivalently. And you see that it plateaus after a while, and because we know the stiffness of the microplate, how much force it takes to deflect it, we can measure the force that the cell is applying on it in order to get this deflection.
Can I ask a question? I mean, what difference between this and the normal culture experiment is that now all the contractor element goes perpendicular?
Yep. Yes, and it allows me. Well, it makes a huge difference for the model, as you'll see, because you can decouple the spreading from the rigidity sensing.
Okay.
But you'll see more about this geometrical detail. We can come back to that. So the advantage of that setup, first there's a direct readout of the force in the vertical direction. You don't need an inverse method to do that, so that's sparing you a lot of effort and uncertainties too. The material with which the cell is in contact is always glass and always coated the same way. There have been issues and questions about, if you change the stiffness of the gel the cell is spreading on, it may change also how it feels. Then the cell scale, well, the cell is really sensing the stiffness at the cell scale. There is no sensing the interference in the focal adhesions because the material is always glass. And also we have simple boundary conditions around that, and the shape is much simpler because you have simply one curvature, and you can actually model the shape of the cells in this microplate experiments much more easily than in these plated cells experiments.
Sorry, excuse me. How big is the nucleus here?
Well, the nucleus is somewhere in the middle.
So eventually you also compress
it. So we are not compressing it. The cell is compressing it because that's the cell which is acting. So in the lowest rigidity experiments, in these cases, yes, the nucleus is being deformed. So, okay, so we can vary, of course, the stiffness of this top plate over a very large range. And then I'm sorry, this is cut. So this is the stiffness here as the x-axis. So we change the stiffness, and if the stiffness is very low, the cell is able to deflect a lot the microplates down to less than half its original height. If the stiffness is very high, up to infinite, so you cannot deflect, cannot reduce the length of the system. Of course, the length is set to 1, and the force plateaus. There's a maximum force that the cell can reach, in red here. If you have a low stiffness, then the cell manages to get to some target length, and you have the force which is proportional to the stiffness, because force is stiffness times deflection. So what was really bothering here is that you could fit that with a very easy phenomenological model. Because we have here, for low external stiffness, a set length, and for high external stiffness, another set length, you could fit that simply with a spring model. If you replace here the cell with a simple spring of an adequate stiffness, which is pre-stretched in the original, in the initial configuration, what you will get is that if the external stiffness is much lower than the stiffness of this green spring, you manage to get back to the equilibrium length of the green spring, and the force will be proportional to the deflection, of course, and times the external stiffness. And if the exterior is much stiffer than your green spring, then you will actually extend it up to a force which is equal to the extension of this green spring times its stiffness, its arm stiffness. So you will get that. But of course, we know that cells cannot be satisfactory in a satisfactory way modeled as a simple spring, because if you use, for instance, a drug that prevents the myosin from acting, then your force goes down by orders of magnitude. So, and I'll show you that a bit later. So we need a more accurate model to go beyond this phenomenological modeling of the cell.
Sorry, but
Yep.
again, if most of this comes from compressing the nucleus, then that the nucleus acts like a spring is
We're not compressing the nucleus. The cell is providing the force. We're not compressing anything. We just set the stiffness. So we wrap the cell between two plates, it adheres, and the myosin action deflects the plates. If you add blebistatin, then the deflection goes down. We're not pushing. The cell is pulling.
It's not a spring in compression, it's a spring in extension.
This spring has its equilibrium shape at the height, at the original size of the cell. So we're not in a compression experiment. It's really a traction experiment in a way. The level of traction is set by the cell. Okay, so let's go towards some modeling of this object. So you need to have mechanical balance. Because we've seen that the myosin was really setting the level of force. It's the tension in the cortex that is susceptible to give rise to the force we measure. Okay, so the model is a thin shell of actomyosin surrounding the cytosol with a definite pressure. I haven't put the nucleus in there yet. Anyway, for small deflections, the nucleus won't be deformed. Okay, we can discuss that later. Then, so you have this force balance on the surface. So sigma is the stress tensor along the surface, and can be akin to surface tension. And even without doing any other assumption than that, you can already get this tension of the cortex everywhere, simply thanks to the geometry of the object. Because of the symmetries, you can actually solve this divergence, integrate it, and get the stress in both directions, because it doesn't have to be isotropic. You can get the stress as a function of the position here, and also the force you measure, and the pressure in the cytosol. Now, if we want to go a little further, we need to put some rheology and relate this stress tensor with the deformations in the material. Now, the deformations in the material, as I've told you, you always have this retrograde flow in the cortical actin. So we want to relate the flow in there with the stress tensor. Because of the symmetry, we have flow only along the z direction, well, along the curvilinear coordinate. And I'll tell you now how I derive some rheology of
Has
this.
this been shown in that experiment?
Sorry?
Has this been shown that you have the flow only in that direction?
experiment?
No, we couldn't do.
The geometry is
No, we
unfortunately
couldn't
for
track that. Well,
microscopy.
what we can do is do turf experiments, and we see the retrograde flow radially here. So it's really a radial extension, and we see that organelles are being tracked along the radial direction. So yes,
There is normal, but you don't see the other direction.
no. Okay, but on average, it has to be okay.
Oh, no,
Are you
yes.
sure?
Yeah.
I mean, at the same time, you must have a cortex. To go up, there must be a cortex, and
Yes,
this also has retrograde flow, which goes in the other direction.
Yes, there is a retrograde flow.
In the normal direction, there will be also retrograde flow.
In the normal direction.
The
you mean-
cortical turnover.
towards the inside. There is, well, actually, we have a few scales of, in confocal microscopy, and the cortex is really in the thin layer, and as you expected, the thin layer of.
See, inside this layer, below the resolution of your microscope, there must be cortical flow.
So inside this layer, I'm not sure. I'm taking an infinitely thin shell as an approximation.
Mentally.
This transverse. Well, but you are at the scale. Well, this is really like the thickness of the cortex is estimated to around 300 nanos.
Yeah, or even less.
So yeah, it's. I mean, okay, it's not the first order.
I mean, like Uli, I'm a little bit confused. I mean, do you think there is a cortical, there is one actin flow on top of the other, so to speak? I mean,
Sorry.
there must be a cortical layer, and then there is this retrograde flow. So is it one layer of actin sliding on another layer of actin?
No, I'm just assuming one layer of actin.
Yeah, but then the retrograde flow would go parallel to the membrane along this direction. I would expect that there would be a normal component, because there will be nucleation factors on the membrane.
So, well, I believe the nucleation is happening as usual in the lamellipodium here, where you have. Okay, you could have. Yeah, all right. You have some maintenance. Yeah, okay. So you have some transverse effects, but I don't think it's the leading factor in the mechanical balance here. Okay, so that's probably a refinement that one could add. Yeah. But usually you don't. Well, I mean, when you're looking at a cell, for instance, in the Burnett experiment, sitting on the substrate here, they have actually tracking of the, they have live microscopy of that, and you see the retrograde flow of these fibers here, and the nucleation is really coming from the leading edge there.
Close to the lamellipodium, the normal cortex is degraded.
I mean, you have degradation. Yes, you have degradation happening here, but the nucleation is mostly happening at the leading edge here.
But you now talk about retrograde flow, which is far away from the lamellipodium in your cartoon.
Yes, but that's also far away from the lamellipodium here. You're farther away from the from the substrate, but it's not so different.
Yep. Okay. But you see, behind the lamellipodium there's a lamellum, which has some similar characteristics.
Yeah.
While in your situation, I assume you have a relatively well-defined cortex at the sides.
Mm-hmm.
So it just would be nice to have some experimental image of this.
Oh, it would definitely, yeah. But that's quite difficult because of the distance. Well, you have experimental issues and that, yeah. But definitely, that's something that we're planning to do. Okay, so in order to get to rheology, let's go down in the scales. So if we have a cross-linked network, the linear approximation would be that the stress and the strain are proportional. And this you can get, that's a very classical proof of classical derivation, starting from the length of a strand here and saying that you have tropic elasticity and looking at the probability density of your R strands. If you add the fact that these crosslinks actually detach and rebind at a very fast rate, which is approximately 10 seconds, then you have some deconnection of this network, and this network will yield when put in tension. Okay, if you have when filament which is bound and gets unbound, then you have some relaxation occurring. And this was done a long time ago for, just a second, for transcendental cross-linked gels, and you get this relaxation leads you to a Maxwell type of liquid viscoelastic material. Yes?
Yes, it's a very elementary question. The probability density of what?
Of these R strands, so the probability density of each vector in the 2D space or 3D. Actually, it's 3D for now. Can restrict it to 2D a bit later. Okay, so so you get a Maxwell viscoelastic model here. This is an objective derivative, so a time derivative of a tensor. You can go back to it if needed a little later. So this gives you actually a liquid-like cortex. And now this is not in accordance to what we see at the cell scale, where we've seen that, for instance, Ulrich just a little earlier was modeling the cells with elastic properties. So there is something to reconcile between the microstructure and the macrostructure. And this is what we're going to, because what we can have is a microstructure which has some given properties, and then emergent properties that come from the energy input that we constantly have in these living materials. So in this bulk here, what we have for energy input is actually the myosin action. So if this crosslink is a myosin, then it will undergo this walk, and it will change its anchorage point along the actin filament at some rate. So that's changing the effective equilibrium length of these two strands here. And if you try to calculate what this gives, you can write a very simple theory that you remove the strand that had some length here, and you add one strand which has a shorter equilibrium length, because there are less monomers between the two anchorages. And this can be approximated with a second derivative. I'm sorry, this is the absolute value of rho, this is the modulus of rho squared. So you have some kind of diffusion, and this yields actually a term which is positive, which has a non-zero resultant, which goes towards contraction. So you can see in this model, you can see that as a negative pressure, which is always there, which gives you the bias of myosin towards contraction of the network. So the modeling with a negative pressure was actually is actually a classical one introduced by Dembo in the 90s. So you have this centripetal pressure leading you to contraction in these networks.
A question?
Yes.
But that's only isotropic if the network is isotropic, right?
Yes. So if the network is anisotropic, then this tensor will have the same anisotropy as the network. So yes, I'll be using that a bit here, but actually, for other situations, I would use it much more. In the FF's experiment, it's not that important, but for when you have stress fibers and things like that, it may be very important. Yes, and very useful. Okay, so let's have a look at how this rheological model behaves. So here I've written it in 1D. You see that there is this actually nonlinear term in the time derivative, which comes from the objective derivative of the tensor. So if you have an objective derivative in an elongational frame, this gives that. I can explain that during questions if you like. And then you put that in mechanical balance with boundaries here, on which you measure some traction. And okay, so we're looking at the flow of a material, which is the actin network. And I will assume that its density is being regulated quite fast. So this time of regulation will be very small, so that the density of actin will be preserved everywhere. Okay. So I assume there is something magical and living that provides me with a fixed density of actin, which is what we see actually. You've seen the movie of the retrograde flow. All the material should accumulate in the middle. It doesn't, because it depolymerizes and is also repolymerizing both at the lamellipodium and possibly at the cortical membrane in other places. But yeah, yes.
The thickness of the cortex is there.
No, I also assume that the thickness is constant. You could assume that's the surface density, which is constant. That would be enough, probably. Okay, so let's play with the boundary conditions here. So first, if I have these boundary conditions of fixed walls, Dirichlet boundary conditions, then the mechanical balance, if I have no other bulk force, then sigma will be equal to would be a constant all across, and epsilon dot, the strain rate, will be 0 because I prevent my system from contracting. So if I cancel epsilon dot and go for the permanent regime, I find that what the stress I feel, the traction stress I feel, is actually the myosin stress. Okay. Right. So cells poor, and that's actually compatible with what we know about cells plated on the substrate. They contract things. They exert contractile force through the myosin. Now, if you put porous boundaries here, what you will have this time is that sigma needs to be 0 because you cannot build any stress if these boundaries that can move. So Neumann boundaries, no force at the boundaries. So you will contract the whole thing because only epsilon dot will remain here, and you'll have an exponential contraction here. And that's actually what you find in gels of actomyosin. They precipitate until steric effects prevent them from precipitating more. And then the interesting case is when you put some resistance of the boundary, so for instance a spring resistance like in the experiments by ETF, and then you can relate the rate of strain and the stress via the external stiffness here, and you have some reaction, which is that if the external stiffness is too high, you have no deflection of this boundary, so it's like a Dirichlet boundary, and you have the maximum force, which is the myosin exerted force. And then if you have sufficiently low stiffness, then this sigma A will be larger than sigma always, and you'll contract until your system reaches 0 height. And so you'll have a force which is proportional to the deflection times stiffness, which is linearly proportional to stiffness. So this actually mimics a little the experiments, but you get a system of 0 length if you have too little resistance to the deflection here, super precipitation of the cells. Now this is not the case in reality. Cells maintain a fixed length, a finite length. So one way to explain that is through another mechanism, which is the actin treadmilling. So you've seen the movie with the actin actually moving centripetally, as I have in this model, but also the edge of the cell was progressing at the same time. So this means that there is polymerization at the edge. So if you have polymerization at the edge of a contracting network, it can, for some given height here, it can cancel out the contraction. There exists a value of h for which, for a given epsilon dot fixed by the myosin action on retrograde flow, you cancel out the increased length of the polymerization. So you have a fixed length, a length regulation through that mechanism. You're contracting but protruding at the edges. Okay? So what does it give? So if you add this treadmilling, so you decouple actually the height evolution with epsilon dot, where you make a difference of the speed of polymerization, added new material at the edges, you find that the length is regulated for small stiffnesses, and you have a very good fit of the 1D model with the experiments here, with just 2 parameters, which don't appear completely. I'm sorry. Well, so you have 2 parameters which are made up of the speed of polymerization here, the relaxation time of the viscoelastic network, its elasticity, and here there is sigma A, the contractility of actomyosin, and you have a critical stiffness there. Now, you can also reproduce, so here you have an idea of the variability in the experiments. That's something maybe that should be stressed also for mathematicians. You cannot expect experiments with the same cells, the same modality, to give you something with a small error bar. You have large error bars. but still, this is a prediction actually based on numbers, the 4 parameters calculated on the global picture for extreme stiffnesses, and then here I take an intermediate stiffness and compare the dynamics. And I find that without any fitting, my model is predicting quite well some average sense of the dynamics of the cells. And then one brilliant thing that they can do in experiments is vary instantaneously the stiffness, the apparent stiffness of the apparatus through a feedback loop I won't explain for lack of time. But what they find in the black points here, which are experimental, that when they change the stiffness from high to low, instantaneously, the cell reacts by pulling deflecting the plates quicker or less quick, depending on the stiffness. And this, the model predicts without any fitting either. So that's like a spring reaction, actually, to a change of the environment. A very intrinsic, direct reaction of the material. Now I can do that in 3D too. I have shown you already the mechanical balance that's the calculation gives in these curvilinear coordinates, a bit nasty. The boundary condition can be applied there. We can then write the constitutive law in these curvilinear coordinates here and solve that for the static situation, simply adding what I was writing here that you have a balance between you have this protrusion at the edges close to the substrate, and you find actually that the 3D model with different parameters fitting, but gives the same prediction as the 1D model actually. So really, in this experiment you have sufficient decoupling between the lateral spreading and the vertical mechanosensing and contraction, so that the 1D model is actually already quite good. And the 3D model is just bringing a tiny refinement in that. Let us note that because of this energy dissipation of contracting the network, so you dissipate energy whenever the myosin works in actually straining the material, you can have different tensions in the 2 directions. So these are the surface tension. This is the surface tension in the 2 directions on the actin cortex. This is the myosin action, which may be anisotropic, but maybe also isotropic. And even if it's isotropic, you can have a different tension because if you have a different rate of strain in the 2 directions. Okay, so now let's. Okay, because I'm telling biologists there that it's all material properties. Mechanosensing is not something. It's just an intrinsic reaction of a material, which is what I see here. I have the same cell put in different conditions, and it gives the same biochemical phenotype again, gives very different morphological phenotypes just by mechanical switching, I claim. Now I can play also with the biochemistry. If I add blebistatin, I regulate the way that myosin is being available for contraction, and what we measure is that the force that the cell exerts on the microplates decreases in a way which is incredibly well fitted by the enzymatic activity of blebistatin. So you add some dose of blebistatin, you look in chemistry how much this blebistatin is preventing myosin from acting, and that correlates, the reduction coefficient is the same for the force you measure. Okay, so this was this point here. I can do that also for the other points for different external stiffnesses. And what I get is that for a different level of myosin, so a biochemical regulation, I have the same mechanical reaction to the change of the environment. So that's a bit as if, okay, so this guy pulls very hard on the pedals, but of course if it's flat with the same gear, then the pedals will turn very, very fast, and he will use up his energy in turning very, very fast the pedals, okay? Whereas when it's very steep, he's going at some rate. Well, he's actually stalling, but he exerts some force, okay? Whereas this guy is pushing less on the pedals, but he has the same reaction depending on the slope he's climbing. Okay, so that was just to tell you about the dynamics. So that's how we fit the two additional parameters setting the dynamics. In total, we have 4 parameters. And this is a kind of 3D map showing that we both match the dynamics here for a fixed height, fixed deflection, depending on the stiffness. So the stiffness would be the angle of these planes here, and the statics. So with 4 parameters, we have the fitting of all these data, which is a rather good fit. And now, because I was talking about this cyclist, let's go maybe to the muscle. So if we plot the force, the contraction speed against the force, okay, how fast the cell contracts the microplates at a given force level, then we are replotting something that Hill did in 1938 with whole muscles. So he would put a muscle in series with a force. He would extend it first, then release, and look at the speed of contraction of the muscle against the force that he was applying. And actually the curve is the same, and that was the surprise of the experimental study. Now, how can we explain that?
You're plotting the force in the 2 plates? Is that the force?
Yes, so actually for the cells, because we set the stiffness and not the force, because they need to adhere before exerting force, we actually measure the rate at which they are contracting when they have deflected the plates of a fixed distance, and we measure also the force they are exerting at that time. So and then we can match the 2 experiments.
Oh,
yes?
The contraction speed for muscle scales with the number of sarcomeres.
Yes, okay, but that's unscaled. So we actually, okay, we have normalized, of course, the things. So what we say that for both of them you find, there are 2 intercepts, which we scale to the maximum force. Of course, bigger guys will have stronger force, okay? But the behavior is kind of universal and was found in all muscle types, and that's this shape here.
I just wanted to understand if the order of magnitude is similar, so to speak.
Oh, no, not at all. You cannot scale up, and these are, well, I'll show you the energy budget if I have time, and you'll see that probably the efficiency is also very different.
I see, but I mean, I just wonder if you could estimate the number of myosin heads and make a relation.
I'm missing numbers there, because we have really experiments only at the macroscopic scale. So although I can predict a few microscopic things, then I'm missing a lot of numbers to estimate that. So, well, it's surprising that the 2 would match when you know that, of course, well, it's the same molecules in there, actin and myosin, but the organization is completely different, and a physicist wouldn't tolerate that disordered system and the crystalline system have the same signature. Well, though, in the modeling, there are similarities. So this is my model, and this is Huxley's model explaining muscle contraction. So his model is that you have the myosin here is pre-stretched before adhering to the actin, and then it will bind to the actin and pull and release. Okay, so that's how muscles work, and that's still the accepted muscle model.
Oh, I don't agree. not the original Huxley model. I mean,
well, yes, that are refined, but that's still the essence of the thing.
One would really write down the exact Huxley model anymore.
No, okay, yeah, but still it's the essence of the explanation of how muscles work. Then Huxley explains this maximum speed that you can reach for 0 external force. So if you have the 2 filaments sliding with respect to one another at maximum speed, what happens in Huxley's model is that the myosin grabs the actin, pulls, but before it detaches, the filament has continued to slide, and so it's being stretched the other way around, and it resists the motion actually. So it's a kind of friction. The distance you travel before you detach is actually setting how much resistance you will put to the motion, and that sets maximum speed. That's actually exactly the same here in this case, because what I have a viscoelastic material. So if I'm trying to have it flow, this won't work if I'm in the elastic regime. So for short times, my material will react elastically. so it will reach a fixed deformation. I have to wait for the relaxation time of my viscoelastic liquid for it to flow. So it's the same reason. It's actually a friction, and you need to detach the crosslinks for the material to fluidize. The other extremity here was not explained in so many words by Huxley, but it's also in his model. This time, you imagine that you have these Dirichlet boundary conditions, so you cannot deflect the plates, the boundaries, and this guy is walking and providing more and more tension. So this tension would go to infinity if nothing happened, but at some stage, this guy will unbind, or that guy will unbind also, whichever first, and this will release locally the energy. So you cannot move the boundaries, that's what you have imposed, but locally you have some dissipation of the tension you've built up in this system. So you have some kind of internal creep that doesn't go to the boundaries but dissipates energy. And actually I have, okay, that was the cartoon for the internal friction, and that's the detachment limited maximum force. So imagine you're bending your oar and you lift it up out of the water, and then it will just dissipate energy by vibrating away. So that's the internal creep I have. Okay, so now because I have only 4 numbers to match, I can, well, I'm sorry again. So this is the force here. So as a function of the force that the cell is producing, you have more or less deflection. So the work rate, of, the mechanical work rate, how much power you give to the exterior is modified, okay? If you have 0 force, so you're pulling against nothing, you're providing no energy to the exterior, but you still dissipate energy. And if you have the maximum force, then it's fixed, you cannot pull, so you provide energy, but you dissipate everything internally. So I'm writing here all these mechanisms, and I try to quantify them. So the mechanical work rate we can measure, so we can measure it after some deflection. That's why there is some difference between these 2 lines, but I can predict that line here. And the parameters, the 4 parameters allow the good fitting with the experimental data. So there is some optimal, of course, for an intermediate force. Here I have, so that's when it's working. Here I have this viscous-like dissipation that you need to fluidize. So you need to actually lift up your oar for limiting, in order to limit the friction with the exterior. So you have some dissipation. If you go very fast, then the time you take to lift up your oar to detach your magazine is actually providing some, well, doing some friction, so you dissipate away energy in that way. Then you have this dissipation due to internal creep, which is larger when you have a strong force and you're stalled, so you should detach before that the tension you've built up is being used to move the plate. And then in cells, you have something different from muscles. You have the work against polymerization. So I've told you that the cells were protruding, and you pull the material again by retrograde flow, by contraction. This has, of course, an energetic cost, which is actually quite large. So it's very sorry for the boat, actually. And that's actually, according to the calculations, that's actually the largest part of energy that goes into maintaining this retrograde flow of this fluid material. So this would look like it's very inefficient. You see it's a broken scale here. So a lot of energy goes into maintaining this retrograde flow that serves nothing, seemingly. But what you can check is whether this total energy input is actually significant or not. And then if you compare it with the cell metabolism, it's like the 1,000th part of the energy that the cell spends per unit time. So it's actually not that costly to maintain this flow, this useless flow, if you see that on the other hand, what this system gives you is that you have a liquid skeleton that maintains elastic-like properties. So I have an emergent property of being elastic-like, which fits with the phenomenological models that we have for cell scale. But being liquid allows you also to adapt your shape quite efficiently and gives you some versatility. And you've also seen this experiment in which we vary the external condition and the cell reacts instantaneously. So that's another asset as a material property. You react to challenges very rapidly because of your own material. You have intrinsic properties. You don't need to adjust and have the pathway. Then, of course, the pathways and the biochemical regulation, as I've shown you, adds up on top of that. And you could have nonlinear things adding up to this model also. But the basics of your material provide you with some versatility and also resilience. So in conclusion, we have some size regulation by protrusion and contraction. This is something that has been seen for a long time. That's now, I think, I think I'm providing some ways to think about it. And it's based on mechanical properties, and it's in interaction also with the substrate. You regulate the retrograde flow by changing the stiffness of the exterior. And at the same scale, you have something behaving like an elastic material, although it's liquid inside. So it's an emergent elastic material. Now, as I've told you, you allow for shape changes through the fact that you're liquid, but you still have this elastic resilience. Then you have these opposite-going phenomena of unbinding. So when you unbind, you may lose energy because you've provided tension, in the case where the environment is very stiff, or you may also allow yourself to flow and to go quicker. So you need to unbind at some rate, and that's a compromise that you make between the two. And actually, I've read more recently that smooth muscles have a very different unbinding rate of myosin, and they're probably less reactive, but they can maintain a shape for much longer than skeletal muscles, which were the ones studied by Hale and Huxley. Now, this is energetically inefficient, but not expensive compared to the metabolic cost, and that provides you a built-in way to react to face mechanical challenges. And then just a little teaser on the fact that that's not the only, the cell scale is not original in that respect. Many organisms have built some ways to react with material properties to mechanical challenges. So for instance, the bee has a pore that is kind of special. So when the bee is sitting on the substrate and there is a gust of wind, it doesn't want to be blown away. So the pore actually unfolds mechanically and adheres further. So it dissipates away the energy of the gust of wind simply by a mechanical reaction without having any muscular reaction. So I'm claiming that you may have that same mechanism at a small scale here. Okay, so now just a word of thanks to my usual co-workers. So this will be Dr. Associates. Guy Blanchard is here and will give you a talk in a month's time if you're still there. That's about Drosophila morphogenesis. And yes, I'd like to also just point for the surface PDE people that we're looking forward to solve these equations on surfaces, and we've done some effort with these PhD students in this direction. So this is seemingly a Drosophila embryo, hopefully, undergoing jumble extension. With that, I thank you.
Beautiful. I just wonder about the role of stress fibers. So I remember in TEF experiments you also see stress fibers. Can you be sure that everything is in the retrograde flow?
So okay. So you see. Well, I don't have the. So you see fibers in this direction, crisscross. It's when seen in turf, it doesn't seem that they that you have structures which are really sitting there, and also the experiment is very dynamic. You don't plate it for a very long time, so I'm not sure you have something like the stress fibers we have, really the ventral stress fibers in.
I was wondering about the ones bridging the two surfaces.
So you don't really call them stress fibers, do you? But
actin cables. But
yeah, so we are really lacking some 3D data.
Yeah, I was wondering your 1D model maybe would be also a good model for stress fibers. Was there
Yes,
also
we.
flowing?
Yeah. So that's also work in progress to try to have a look at it on a single fiber, but as much disconnected as possible from the substrate, because then you have what allowed me really to go that far, I think, is the fact that I could disconnect the substrate interaction from the mechanosensing and the contraction.
Other questions? All right, let's.
So, Eva Paluch was saying recently that with increasing tension on the cortex, it's thin.
When releasing the tension?
No, with increasing.
When increasing, yes. Yeah. Well, so here where really the modeling was done with an assumption of infinitely thin, but still with an asymptotically thin cortex. I think really we should go deeper into the modeling in order to see this type of effect. I don't think this model is sufficiently detailed on that scale to go to this type of effect.
All right, let's take a picture again.